Hello, good afternoon. Thank you for coming. So I decided to reorganize this a little bit. Just a second. We have to control this situation. Just a second, please. Okay, no. Hello? 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 Yeah, it's okay. Thank you. So hello and welcome. I decided to reorganize things a bit. So today I'm going to finish the introduction to the theory of stability of Lyapunov. But you know, when you go through Lyapunov theory of stability, if we introduce it through motivating examples, it seems that each case is a new case. So is there any order in the universal scheme of things? And that's why I decided to, after this, then I'll stop a little bit and revisit the linear world, because I think it's very important. So in many circumstances, we can linearize the system and design controllers, and therefore I'm going to cover something that is called LQR, linear quadratic regulator, which is very important, and how that degenerates in some cases in PID controllers. So almost everyone knows about PID controllers, but sometimes they miss the intuition, and the intuition is very, very, very important. So after this and the PID and the LQR design, I think you'll be in better shape to understand how the design of more complex systems is done. And then I'll cover some path following, then cooperative, and then I'll get into navigation. So let me remind you of the fact that using Lyapunov theory of stability, the whole problem boils down to wanting to show that the trajectories of the system converge to the origin, because you did a coordinate transformation and everything is referred to this origin. And again, what I want to impress upon you is that you don't have to solve the differential equation to show that the trajectories actually go to the origin. That's the magical thing about Lyapunov. So again, I remind you that we construct this Lyapunov candidate, inspiration, a menu that you have on in your head, intuition, whatever. And then we try to compute the rate of evolution of this energy-like function. So remember, this is not necessarily energy. That's why I call it energy-like function. And the way this is done is very simple. I showed to you. So that's where we were at. So let's move forward, because I covered this already. And I gave the formal definition of stability and attractiveness. And then I was essentially quoting a major result that I did not prove, which is the following. So suppose you have an equilibrium point. Let's call it 0. All right. And you have a differential equation. It could be a mechanical system, electromechanical, whatever. And you want to answer the following questions. So if 0 is an equilibrium, what do I mean by 0 being an equilibrium? If you put 0 there, the derivative is 0. Everything stops. Okay. If you can find this cup-like function that is called positive definite, and such that the derivative along the trajectory is less than or equal to 0, the origin is stable, not asymptotically stable, it's stable. If, however, the energy or energy-like function actually decreases along the trajectories, then the trajectories converge to 0. It's a very, very powerful result. These results are all local because in many cases we can only show that these things hold in some domain that is not the whole space Rn. But if the energy-like function actually is like a paraboloid in many dimensions that blows up to infinity as we go further and further away from the origin, then you can show that no matter where you start, you are sucked into the origin. So that's what we call global, globally asymptotically stable. So this was the magic result. There's something that maybe it's a bit trickier to understand, which is the following. Okay, so I have shown you that if v dot is less than or equal to 0, on the first shot, you cannot conclude that the trajectories actually go to the origin. Okay, they don't blow up, but they don't go to the origin. So the question is the situation hopeless when you can only show that the derivative is less than or equal to 0 and not strictly less than 0 as we would hope for? Not necessarily. Now, deriving the result that I'm going to mention to you, it takes a little bit of a work. It's part of dynamic topology and stuff like that. But the basic idea boils down to the following. Okay, so I could only show that the derivative is less than or equal to 0. Let's not panic. And we asked the question, all right, let's look at the points where the derivative is actually equal to 0. There's more than one because it's not only at the origin. But let's call that set of points gamma. So very easy. dv dt less than or equal to 0, where is the set of points where the derivative is actually 0? That is spoiling the whole thing. Great. And now you imagine this thought experiment. So omega could be a line that includes the origin. And now you imagine yourself sitting on top of that line and you let the system go according to the dynamics. If you can show that no matter where you start, you will leave that line, and the only point at which you start such that you don't leave that line is the origin, then still you get asymptotic stability. So this is a very, very powerful theorem. I mean, in mathematical terms, it's stated differently, so don't worry about that. People call it Krasovskii-LaSalle, sometimes it's LaSalle. I believe it's invariance theorems, something of that kind. So it's a bit cryptic. So let's figure out how this works. So an example, suppose you have, so I'm going to do this slowly, a mass spring dashpot system. Now, yesterday I was a bit concerned because someone told me that maybe some of you are not even familiar with the model for the spring mass dashpot. I'm not sure. Is this true? Have you played with this model before? Yeah, okay, fine. All right. So you have a mass, a spring, and the dashpot. And as you all know, when you pull the mass, then a spring recoils through a coefficient. This is called Hooke's law. And so by exerting a force in the opposite direction that is proportional to the distance, not proportional, it's a function of the distance. Now, please notice that I wrote explicitly that the spring, the restoring force, is K of Y, not necessarily K times Y. So we are not necessarily in the elastic region. But one thing we know for sure, this function is in the first and third quadrants. We also know that when we have a damping system or a damper, then the force is related to the speed at which you move. So that's what I have there. It's a function of the speed. So it's not F times the speed. And then you put these things together and you get the sum of all forces, which is the force generated by the spring, by the damper, is equal to the mass, second derivative of y, and acceleration. Now, many times we like to write this in matrix form. So this is a second order equation. But in controls and system analysis, we like to write everything in the form of a single order differential equation, first order differential equation. So we do the trick. If you have not seen it before, it's trivial. So it's a second order equation. So you know very well that if you stop at some point and you need to predict the future, you need to know the position and the derivative at this point. And then if you apply force, you can know the future. So the position and the speed are what we call the state of the system. Why? Because it embodies all the information that you require to know the future. Okay? So everything is very deterministic in this setup. So it's not quantum control engineering. We are not taking care of that. All right. So how do you cook up the state? Normally, we call the state X. Sometimes use bold X or whatever. So X is obtained by putting Y on top of the derivative, and you get the vector, it's the vector S. And of course, in this case, the equilibrium is obtained when we have 0, 0, because if you have 0, 0, well, you know, everything stops. And then this gives you a nice way of compacting the information, because now you go to the first component, which is called x1. So the derivative of x1, which is the derivative of y, is the second component. So you write here. Yeah. So the derivative of x1 is x2. It's true. The derivative of this guy is that one. And then the derivative of x2, which is the second derivative of y, and you go here, put the m there, then you get minus 1 over mk of y, which is x1. And then here you have minus 1 over mf of x2. So you see, now, if you blink your eyes, when you open them, you don't see this thing with the elements, with the entries, but as a vector, you call this dx dt. And this thing on the right side, you call a function of x, which has two components. So you went from a second order system to something that looks like a first order, except that it's in vector form. And this is very, very common in practice. So you get dx dt equal to f of x, and of course, f of 0 is equal to 0. So now you'd like to show, which for this case, it's fairly obvious, that when you excite the system and start outside, okay, and when you start outside the origin, am I brought back to the origin? Well, the intuition tells you so, because you have a spring in the first and third quadrants, you have a damper function in the first and third quadrant, so it should be okay. But let's show it. So if you want to use Lyapunov theory, you start by computing the energy associated with this system. So you have kinetic plus potential energy. So the kinetic energy, of course, it's 1/2 f of m times the speed, and the speed is x2 square, speed square, of course. And then you have the potential energy. Probably you are used to seeing this when the spring is linear. So we have k times y, and the potential energy is 1/2 of k y square. But because k is a function of y, then you actually have computed in this form. So v of x, when you reach a certain position x1, the potential energy is the integral of k of psi d psi, where d psi is the running variable. So that's the potential energy that generates the integral into 1/2 of k x1 squared when the spring is linear. So now you have to be a little bit more sophisticated here. All right. I'm going to assume, because this is the physical reality, that F and K are on the first and third quadrants, and furthermore, they go through zero. When you write this energy function, it's obvious that Vx is positive. This term is positive, and if you think a little bit about this one, it's positive. It is certainly easy to see when the spring is linear, because you get 1/2 of k times x squared, x1 squared, so it's positive. So it turns out that this is a good candidate for a Lyapunov function. It's what we call positive definite. So now comes the next question. How does the energy evolve as time goes by? And remember what I told you, it's very easy, because you have the time, you have the trajectories that are given by the evolution of x1 and x2. And based on these two variables, you compute the big V. So you go from R to R2 to R. So when you compute the derivative with respect to time, first you do the partial with respect to x, and then you do the x dt. So it's the inner product of the gradient times the vector field on the right. So what is the gradient? Okay, so when you compute the derivative with respect to x2 here, you cut, so you get mx2, and then you multiply by the x2 dt. When you compute the derivative with respect to the upper limit, you get the integrand evaluated at that point, and then you get dx1 dt. And now you substitute dx1 dt there and dx2 dt there. So when you do this, okay, that's what you get. mx2 dx2 dt, but dx2 dt is this stuff that you put in here. And then you have kx1 dx1 dt, but dx1 dt is x2. So there are two things that cross, and then you get minus x2 fx2 less than or equal to 0. Now, there's a very subtle point here, because I told you that f of x is in the first and third quadrant. What does it mean for a function to be in the first and third quadrants? It means that x times the function itself is less than 0. So you could arrive at this point and say, aha, this is always negative. Okay, but the x1 is not there. So there are a bunch of points out there, except the origin where the thing actually is not negative. It's less than or equal to 0. All sets of points for x2 for which x2 is 0 give you 0. Okay, so when x2 is 0, which is the plane here or the line here, for all those points, you get x2 times f of x2 equal to 0. It's not less than 0. So it's a subtle point, because you may feel tempted to say that this is less than 0. So in fact, it's less than or equal to 0 when you consider all trajectories consisting of x1 and x2. So you don't satisfy the theorem of Lyapunov that you would like to satisfy, and that if in fact this were less than 0, you'd be done, but it's not. So now you have to invoke LaSalle's principle. So remember what I told you. Don't panic and look at the set of points for which the derivative is 0. Well, the derivative is 0 when x2 equal to 0. So this means that you are having this line there. That's the omega set that I mentioned before. So let me recap. You compute the energy-like function, you compute the derivative, and you arrive to the conclusion that the derivative is less than or equal to 0. No panic. Let me look at the set of points where the derivative is 0, and you plot them. It's the set. It's the horizontal axis. And now remember what I told you. Now imagine yourself sitting anywhere on that line, and you follow the dynamics of the system and see what happens. So, okay, so let's do that. Examine the dynamics if you stay here. Now, at this point, you have x2 equal to 0. So you get dx1 dxt equal to 0. And dx2 dxt is equal to minus 1m k of x1. So what does this mean? That if you start at that point, x1 different from 0, dx1 dt is 0, so you don't move sideways. Okay? And this also tells you that the derivative of x2 is minus 1 over m k of x1. So if x1 is positive, k of x1 is positive, this is negative. So in fact, if you are here, you move down. Immediately go out of that set. You can equally show that if you start on the left-hand side, then you go up. So for every point that you pick, except the origin, if you start there, you are blown out or blown off. The only point at which such that if you start there, you stay on that line is 0. And therefore, from LaSalle theorem, the origin is asymptotically stable. So this is, I think, a nice example to understand this theorem of Krasovskii-LaSalle. Okay, very important one. So let's do a simple example. I gave it this pompous title, but AUV position control. It's just a sphere. It's just an AUV like a sphere. Or an ROV. And suppose you want to inspect something near, I'm embellishing this a little bit. You want to inspect a certain structure. So you want to do very precise maneuvers. So what you have? The derivative of position is speed. And then the acceleration, what forces do you have acting upon the system? U, which is the force generated by the thruster along the x-axis. And then you have the drag that I'm going to assume is of this form. It's a quadratic form. So that's it. This is your model. So when you go in that direction, then the drag force pulls you in the opposite direction. So here is something you want to expect. You stay at a certain distance. This means that you want to move in a very smooth manner from any point to x star. X star is a fixed position. So the question is, how can I drive the position of this vehicle to x star in a smooth, controlled manner? That's the problem. So the way we approach this, so how do you do this? So the way we approach this is the following. I'm going to give you the intuition first. So this is the system, okay? So let's not get lost here. You have x, the derivative of x is v, or in other words, x is the integral of v. And so this is the kinematics. And the dynamics are dv dt equal to minus, and this is the drag plus the force. So it's a very simple case of dynamics and kinematics. Okay, now, it's clear that if you want to drive x to a certain position x star, you have to compute the error and drive the error to 0, right? So you subtract this guy from that one, and this will give you the error. Remember, the basic step in controls design, you have to find the variable that you wish to drive to 0. So you want to drive this to 0. So a very naive way of doing this is you compute the gain, you compute the error, multiply by a gain that you have to choose. And then based on this error, you send an input to the thruster. So when the error is very large, then you send a large force. When the error is very small, then the force becomes smaller and smaller. I'm also going to do something interesting, which is on top of this, I'm going to also to have a feedback loop that feeds on velocity. And you know that if you have a gain that multiplies by velocity, this is like a damping term in the mass spring, the dashpot. So here I'm being motivated by what we call a proportional and a derivative control law. And then I'll get into this in more detail. From a physical standpoint, it makes sense. So when you have a problem like this, you have to compute the error. The simplest thing you can do is to multiply the error by a constant and you drive it. So the larger the error, the more force you are going to put there with the appropriate sign. But hey, you also want to control a little bit how this thing is damped out. So introduce some virtual damping there. All right, so the big question is this going to work? Because this system is nonlinear. So we don't know how to analyze with the classical tools. So you go here. So very important, what I mentioned to you. Start by looking at the variables that you wish to drive to zero. And in this case, you want to drive to zero the speed, v, and the error, which is xt minus x star. I guess I called it x star minus x, doesn't matter. You can define it in this manner. X minus x star should go to zero. That's what you wish to do. So in other words, we want to generate the force here such that the error goes to zero and of course the velocity goes to zero. Okay. So let's write. So the next step is you write the dynamics for the things that you want to drive to zero. So dv dt is, of course, comes from the dynamics, drag, and the input. And what is dE dt? It's dx dt minus dx star dt, but x star is fixed, so it's zero. So dE dt is v. So these are the equations of motion. And now let's assume you make u equal to what we proposed before, minus k1 minus k1 times the error or the symmetric of the error or whatever, minus k2v with k1 and k2 positive, and you stick them in there. So what you get? The v dt is equal to drag force plus u, and u is minus k1 times the error minus k2 times the speed, and the dt is v. So, all right. All right. There you go. You know, when you break these things into two, it should remind you of what we did here. You see, dx1 dt, x2, dx2 dt. So somehow now the error is playing the role of x1 and the velocity is playing the role of x2. Remember, something equal to the other variable, and then the derivative of the other variable is something else, which is exactly what you have here. Derivative of this is the other variable, the derivative of the other. So, and this is why it is important now when you face a control problem to do some form of analogy with things that you know. When this shows before your eyes, you think, well, there is a spring, a mass and the dashpot system that look very much like this. So E was, in the case of that system, the position, and V was the velocity. And in fact, zero is an equilibrium point. So now, how do I show for this particular case that the error goes to zero and V goes to zero? Let's build this candidate Lyapunov function. And it's here that you see for the first time that you seek inspiration from the mass spring dashpot. And even though this has nothing to do with the spring or whatever, because the form of the equations reminds you of what the mass spring dashpot were, you are inspired to derive a Lyapunov function that looks like the other one, except that E plays the role of the deflection. And of course, this one plays the role of the derivative of the deflection. So in this case, you are inspired by this and write. So this is an inspiration. Okay, I'm going to consider the Lyapunov function candidate, which is 1/2 of v squared, and a term similar to the other one, 0 to y of k1 psi d psi. Remember that here you didn't have to do k1 as a function of psi, because the term that is equivalent to the spring is k1 times E and not the function of E. So this is crucial. So whenever you have a problem that you wish to study, and especially if it is second order system, always bear in mind what the equations look like for the mass spring dash pot, and try and establish that energy to help you build up the candidate Lyapunov function. So obviously this is greater than 0. Now this is out of place, of course. So now you have to compute the derivative, which is dv dt plus dv with respect to E dE dt. So the first term, which is the partial of capital V with respect to small v, is v, and then dv dt. And then the partial with respect to the upper limit is the integrand computed at the upper limit, dE dt. And now, because the E dt is v, you put it there. And you know that dv dt is that thing. So you stick it in there and you cancel whatever you have to cancel. And you get minus v squared v minus k2v squared. Remember that when v2 is different from 0, when v is different from 0, this is negative. And you may be tempted to write on the right less than 0. But for the same reason, when you are on the plane, you also have to look at E and V. So this means on the line where V is 0, at all these points, the derivative is 0. So it's not only at the origin, and that's why you have to write less than or equal to 0, okay? So at this point, you cannot conclude that the trajectories will go to the origin. In other words, at the AUV, you actually go in a smooth manner to the final point, but you use LaSalle theorem, exactly the same way I did for the mass spring dash pot. And you can show that the origin is in fact globally asymptotically stable. All right, so that's how you do this. So now let us revisit the problem of AUV path falling that I mentioned to you with a very simple example. So again, there is an AUV. There's the body axis, xb and yb. The velocity vector is aligned with the main axis of the vehicle, so there's no side slip. And there's the heading angle, the angle between north or this axis and the xp axis of the AUV. So what do you wish to do? Suppose you keep the magnitude of this vector, all right, always aligned with xp. Then the only thing that you can do in order to steer the center of the vehicle to the path and make it follow the path is by controlling the heading angle. So set the speed of the AUV equal to a constant and recruit the heading angle such that the lateral distance gets down to 0. This is what we call path falling. And these are very important maneuvers, for example, for ships when you want to go over lanes and you want to do this in a very controlled manner. So you have planned the route for your ship. So suppose it's a straight line. That's the simple case that I'm considering here. And when the AUV starts off, or the ship, as you wish, then it should be able to steer itself smoothly and go along this path. Remember that the kinematic model is very, very simple because it tells you that dy dt is v times the sine of psi. So it's the projectionist vector along the y component. So it's a model. It's a kinematic model where the input is psi and the output is the distance from the path. Again, it may bother you that I'm calling psi an input. If you have a boat, normally you may try to control psi. So psi, you call it an output. But at the kinematic level, this is the variable that you are using to steer the vehicle along the path. And later, when you declare what the psi should look like, for example, starting at 0 and then going to pi over 2, then you have to develop a control system inside the ship that will make the actual value of psi go to the desired one. That's dynamics. That's what we call the inner loop control law. So remember that we started by linearizing. And I told you that for small psi, you can psi in radians and the sine of psi are basically the same. So dy dt is equal to v psi. It's a linear model, and we went through this process. When I first presented this, I said, well, simply take psi equal to -1 over v multiplied by y. That was it, okay? But you see, if this number is large, then the psi may start going through large excursions. So why not saturate it? So you could have the v inside, in fact. It looks a bit awkward on the outside, but you are trying to saturate so that the angle of psi, the absolute value does not go outside a certain desired boundary. For example, no more than 45 degrees. So the saturation function looks something like this, right? So if your angle exceeds a certain value, then you saturate in this direction, and then it's saturate in the other direction. Notice that this saturation function satisfies y f of y greater than 0 when y is different from 0. But now this is a nonlinear system. How do we actually show that y goes to 0? So you do the computations. Now you view this as a nonlinear system, right? dy dt is minus a function of y, and you call this a function of y here. All right, it's nonlinear. So in order to show that y goes to the origin, you have to use Lyapunov. Okay. And this is almost trivial because it's a first order differential equation. So I can start by using a Lyapunov that is trivial. It's like the parabola, 1/2 of y squared. Check that v is positive definite. Yes, of course. I mean, it's always greater than 0 unless y equal to 0. And in fact, v of 0 is equal to 0. And that check that dv dt is negative definite. Well, when you do dv dt here, you get y dot. But y dot is minus f of y. So you get y f of y, which is always positive. So this is negative and you are done. So you get less than 0. You get stability. And now I remind you that I basically told you that if the candidate Lyapunov function is what we call, it has a strange name, radially unbounded. In other words, when x is large, v blows up to infinity, then this is global, no matter where you start. Well, this is not exactly true because I started by linearizing the system. So I'm not being too rigorous here. But from a purely theoretical result for this model, no matter where you start, you are driven towards the origin. And you know, this is a very trivial, a very simple path following control systems. There are others far more sophisticated. I hope I'll be able to mention some, but I don't want to bother you with too many mathematical details. But rest assured that for all of those systems, we show convergence and stability using Lyapunov. That's what we use. So now let us revisit the case. Yeah. It's up to you to decide. Now remember that the saturation is only on the psi, it's not on the y. It's on the psi because you have psi, it's the psi that you saturate. So in other words, you don't try to do crazy things like boom directly to the path. You do it smoothly, okay? But it's up to you to decide. You have a problem. Yeah. Yeah, normally if you have something that works well when you are inside a certain tube of values, the first thing you have to do first, even without using any closed loop control, you sort of nicely bring it into the region. There's no way why you can have the ship move and slowly rotate, and now you engage the path following control. Yeah. Okay, so I wanted to revisit the cooperative motion control. So remember there's this guy going at a fixed speed, V star, and then the other guy maneuvers to stay on top of this. So again, you want to drive the error to 0, which is Z2 minus Z1. So you have to find a differential equation that dictates the evolution of the error. So you get, and this I have shown to you before, dE dt is V2 minus V star. That's it. Oops. I don't know. Okay. That is a problem here. Yeah. This parenthesis should not be there. So remember I told you that if you want to drive error to 0, you choose V2, which is the speed of the quad rotor. That will cancel, and then you put an extra term, which is minus k times the error. So when you are very far ahead, the error is positive and the velocity recoils, and the other way around, then it moves forward. And you get this nice equation, so on and so forth. Now, what's the problem with this? It may very well be that when E is very large, for a certain values of K, you are requesting the V2 to do very large, or even the velocity may go negative. Or when E is negative, then you are telling V2 to go at the speed of light. Okay, that you cannot accept because your vehicle has a certain region of operation. For example, suppose that V2 should always be between V2 max and V2 min, all right? So that's certainly the case for a fixed-wing aircraft because you want to keep a certain speed with respect to the fluid. It's not inertial, but anyway. So you cannot simply use the thing as it is. So remember that when you design this system, something cropped up. Okay. So V star is here, V2 max is there, V2 min is there. This doesn't necessarily have to be in the middle. So there's a delta upwards and the delta downwards. So when you add to V star minus KE, you should stay in this region so that you don't cross the boundaries and you respect the constraints. Oh. So what you do, you make V2 equal to V star minus F of E, where the function looks a bit weird, but depending on the error, you saturate to the upper limit, no, it's not the upper limit, it's the maximum difference positive or the other one going the other way, right? So you have up and down. And if you shape the function like that and add V star to it, then you can be sure that the total speed will stay within those bounds. So now in fact, you have a nonlinear system because you have dE dt equal minus F of E. You no longer have simply K times E. So is this going to work? Well, you know, you use a Lyapunov function and have a v square, you do the derivative and everything works to perfection because E f of v is greater than 0. So it's another very, very simple application of Lyapunov theorem. Okay, now there are some refinements. I don't want to bug you with too many mathematical details at this point, but it's important for you to bear this in mind. So remember I told you when you have a candidate Lyapunov function, the computed derivative, it is less than 0, beautiful. When it is less than or equal to 0, you have to use Krasovskii-LaSalle. But that's in the case of time invariant systems. Sometimes people call them autonomous systems. There's nothing to do with autonomy of robots or whatever. It's a mathematical term. So what do I mean by this? It means that when you go to one of these models, where was it? For example, here, none of these coefficients is changing as a function of time. Like, for example, you have an aircraft that is carrying fuel, then the mass is going to change as a function of time. Or the aircraft is going across different layers and the drag is going to change. That's a non-autonomous system because it's time varying. Okay. Krasovskii-LaSalle does not apply to non-autonomous systems. So, and this is a big thing. So what do you do? When you have time varying systems, you have to work a bit hard. And you use something that is very funny. I mean, the name is funny, Barbalat's lemma. And Barbalat's lemma, in its essence, it's such an interesting result because it revolves around something that may be unexpected to you. I don't know. You guys are brilliant guys. You know all about mathematics. You can have a function going to 0 and yet the derivative does not go to 0. Are you aware of this? Yes or no? I'm curious. You may have a function going to 0, but the derivative of the function with respect to time may not go to 0. Not necessarily. You know this? Yes? Wow, wonderful. Okay. So if you have a differentiable function that has a limit, under certain circumstances, the derivative goes to 0. And the circumstances are dFdt should be uniformly continuous. Oh, now we have a problem. What's this uniform continuity? But you guys know this, right? So remember the stuff about continuity. How do you prove continuity? For every epsilon, there's a delta such that blah, 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 as a function of delta, then I still that delta as a function or as delta does not change with time. It's all uniform. That's uniform continuous. But don't bother because a simple sufficient condition for a differentiable function to be uniformly continuous is that the derivative be bounded. And Barbala's lemma builds upon this simple thing. If you have a differentiable function that has a finite limit and dFdt is uniformly continuous, then the derivative goes to 0. So how does this work? So if you have a scalar function that is lower bounded, it's negative semi-definite. In other words, it's not necessarily less than 0. And if dVdt is uniformly continuous in time, this is applying Barbala's lemma, then the derivative goes to 0. Okay, let's give an example. So you have the vehicle, the ROV, the AOV moving in the water. I'm increasing a little bit the complexity of the topic, just, but I don't want to dwell into this too much. Just be alert, because when you have non-autonomous systems, life becomes a little bit more complicated. And this happens in path following control systems. So now suppose that the only change is derivative of position is velocity, derivative is position, and now you have a very time varying direct term. Don't ask me where this comes from. I have no idea. I just invented it. It's a time varying direct term. So can I still show that everything works well and with the control system that I had, the ROV will go to the desired spot. So I'm going to do this quickly now. So you see the difference. This is the old stuff. And this is the new stuff. The only difference is in the A that is changing with time. You still go for the same candidate Lyapunov function that is inspired by the energy for the mass spring dash part. So the equivalent of kinetic, the potential, and when you do the derivative, now you get minus AT V square. And of course, this is always positive. This is positive, less than or equal to 0. You could say, now apply LaSalle's theorem. You can't, because you have a time varying thing. So when you compute dVdt, you get this thing over here. And now the reasoning is a bit, it twists a little bit your neurons. So you have dVdt less than or equal to 0. Now pay attention to this. So you have a function that is lower bounded by 0 and decreasing. Not strictly decreasing, it's decreasing. If that is the case, then V has to converge to a finite number. There's no way. And if this V, oops, and if this V converges to a number, then V and E remain bounded. They don't blow up. They don't blow up. Moreover, it's easy to see that the second derivative of this guy is bounded. I mean, just compute this, blah, blah, blah. So if you have a function that converges to a finite number, it is uniformly continuous, and the derivative is if it is uniformly continuous, then the derivative tends to 0. Now, okay. If the derivative tends to 0, this means that V tends to 0. So you have shown that V tends to 0. What about E? Does it tend to 0? You do another argument, and then I'm not going to get into this. It's there in the slides. And yes, E converges to the finite value. So you play this game, making sure that V converges, that it is, the derivative is uniformly continuous. Then you obtain that the derivative actually goes to 0. And then you look at the derivative. If this goes to 0, V goes to 0. And then use some more reasoning and you show that E goes to 0. That's how you use this this Barbala, the famous Barbala lemma. Okay. I thought of talking a little bit about this, but my God, you are probably not familiar with this notation. So I shouldn't cover this because it would only mess up things. Okay. It will be there in the slides if you are interested, but I'll tell you what the idea is. And this is very important, by the way. You know, when you deal with the classical control, you talk not only about stability, but you may ask questions. For example, if I drive this with an input that is a step, what will the output do? I mean, what kind of shape? Does it wiggle a lot? Or if I stick in a disturbance, for example, in the rudder and in the torque, will my control system be able to kill that disturbance to the rudder? Especially if you made a mistake in installing the rudder and it's biased. So you think it's at 0 and the torque is 0, but in fact, it's giving you a certain torque and you should be able to kill that thing, right? Okay. So the behavior of the system with respect to external inputs and disturbances is very, very important. Now, there seems to be a big gap here because when I talk about nonlinear systems, all I'll talk about is having the trajectories brought down to 0. Where is the behavior? How do I know if I'm going to reject some disturbance? How do I react to input, so on and so forth? And it's only fairly recently that people started getting results. In other words, when you have a nonlinear system, being able to answer the following question. If I have a nonlinear system that starts somewhere, and if I drive with a certain disturbance, how can I be sure that the solutions will naturally decay and that the input is going to have a very small impact on whatever the system is doing? And this calls for the concept of input to state stability that I'm not going to dwell into this, but just be alert, there are beautiful mathematical tools out there that will allow you to ascertain if yes or not you can do these wonderful things, okay? So I'm going to close the nonlinear stability theory, and now I'm going to go back to more classical stuff because it's important to give you an idea when we design control systems in the linear world that the intuition plays such an important role. And yet, when you have complex systems, you cannot solve things by hand. You have to have a systematic way of doing this. So I'm going to start by reviewing the PID control law, but bringing our attention to a number of details but maybe some of you have never played with PID control, right? I don't know. Huh? Okay, good. So you learn about this. And I think you learn the good way. It's not only you'll go through the intuition. And then I'll ask you the question, well, okay, so when you have a complex system and you want to do control systems design, what can you do? So I'll guide you through a beautiful tool that is called LQR, Linear Quadratic Regulator, which is beautiful and very elegant. So I'll cover that. So I'm going to stop for about 10 minutes because now the next part I'll write on the board. So I have to do the transition here. So please bear with me for 10 minutes or so, okay? Thank you.
Just one doubt. So till now the only nonlinear control we learned is the saturated control only.
No, I showed you cases in which what is important is the nonlinearity. It could appear in the dynamics, as I've shown to you. It could appear in the control law, like in a saturation, but it could appear in many other things. I just gave you some relatively simple examples. But the essence is, if you have nonlinearities in the dynamics or in the controller, or both at the same time, then you should use these tools. Yeah. But not in the control, it's not necessarily as simple as, for example, there's a branch of theory of control that is quite nice. It's called sliding mode control, and that's highly nonlinear. The structure of the controller itself, right? And then you have to use Lyapunov tools, Lyapunov all the time, okay? So there's still much out there to be learned by God, so many things, right?
Like, when do we transition from linear control to nonlinear? For example, here you showed my state variables can blow up. That's why we introduced saturation. So that
no. I introduced saturation because I started with a very simple control law. It's important to understand this. I guess it was here. You see, when I first did this before, I simply said, well, let's understand the problem. You have the vehicle going at a certain speed and the velocity vector is aligned with the main axis, so no side slip. So if you want to orient yourselves towards the path, all that you can play with is the heading angle. And I'm assuming that you can control the yaw angle. Hey, go to 30 degrees and boom, it goes immediately. Okay, something like that. Then you have to worry about the other problem. And when I first presented this, I simply did psi is equal to -1 over v times y. So in the end, you got a differential equation, which was dy dt equals to -k times y, goes exponentially. But it may very well happen that when you do psi equal to -k times psi or times y, that the psi will become very large, and you are not interested in that. For example, you don't want something foolish like if you are far away from the path, the y is large, and suddenly the psi starts rotating all over the place. So let's keep it nice and small. That's why I introduced the saturation. Okay. So it was a strategy to avoid the psi going berserk. Okay. And any other questions about this? Are there any questions from the audience, please? Oh gosh, I have them. No. Ft equal to sine of, is it the square root of 1 plus t? Well, thank you. In fact, I don't recall any function that behaves that way, but I know it's possible. So thank you if that one is an example. Any other questions from those that are attending remotely, especially from Avanish? No? Sarojni? Yusen? No. I hope you guys are still alive and kicking. So you have any other questions at this point, or should we go and see the monkeys? Okay, thank you. Okay, thank you, Avanish. See you soon. All right, now how should I do this? Because I'm going to write there, but I should still leave this on, right? Yeah. with the oh. With a soft introduction to what we call PID control. Now, some of you that are familiar with PID control may react, well, you know, that's classical, that's trivial, but you learn so much by going into the guts of PID control laws that it's very important to understand what's going on. So I'm going to start by considering a very simple system, which consists of a ship going at a certain speed, and then it has a rudder that deflects. And this is going to impart a torque that I call U about the z-axis. And then this is going to make the vehicle rotate, or the ship rotate, at rate R, okay? Now, we are not going to get into the modeling of this system, but there's a very simple model that is called Nomoto. Nomoto, I call it number 1. That is very simple. It tells you, well, of course, here you have R dot. So everything comes from the equation. The sum of all torques is the moment of inertia times the angular acceleration, right? So the sum of all applied torques. I'm still learning how to operate with this. Okay, the sum of all torques. So what torques are we involved here? One of them is due to the rudder deflection. So U, rudder deflection. Then it's going to generate a torque. And the other component has to do, and we are going to adopt a very simple model for the rotational drag that sort of slows you down. And I'm going to make it linear, minus a coefficient times R. So as you try to rotate fast, this thing slows you down. So this is great. Okay, and now you simply write this R dot is equal to minus A times R plus B times U. I'm not telling you what the A and B's are. I mean, they come from these things, so no important. There's an A and a B, and both of them are positive. Oh, participants can now see your screen. Okay, fine. So simple Nomoto model, number one. And notice the interesting thing, not a very simple thing, when you put the rudder equal to 0. Okay, when you put the rudder equal to 0, this thing gets squeezed down to 0, and you simply have R dot equal to minus AR, which means that R of t is equal to original rate of rotation e to the minus AT, A greater than 0, and this is for t greater than or equal to 0, right? So there's a natural damping. There's a natural damping. So you should get used to the fact that one should associate this A with some form of damping, because it's dampening the response in your rate. So this is the very simple model of Nomoto. So when you have a ship, you go at a certain speed, you deflect the rudder, the thing starts spinning, and you ask, what is the model? In some cases, this is a good enough model. So now suppose that instead of looking for rate of rotation, I can actually try, I actually want to try and find out what the angle psi is doing. So we are led to Nomoto number 2, where the only thing that you do is go to the old scheme, R dot, and here you have A minus and BU. And now you say that psi is the integral of R. So that's the Nomoto model number 2. Okay. Then of course psi dot equal to R. And the question is, when you have the input, which is the rudder deflection or the torque generated by the rudder, for example, and if you want to control any of these guys, the Nomoto number 1, the Nomoto number 2, what does it mean? It means that in this case, I want for the ship to reach a certain rate, a certain rotation rate. And in this case, I want for the ship to achieve a certain angle. So now I hope I'll be able to get this right. Boom, 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 boom. Beautiful. I'm on number 2. Okay, great, great. So suppose you have this simple model, R dot equal to minus, I was going to erase with my hand, minus AR times BU. So how do you make R go to a desired value, RC? So RC is the desired value, desired. R is the actual value of R, and you want to make E equal to RC minus R go down to 0. It always boils down to this thing here. So now if you have this model, and I'm going to redraw it very quickly. B U R. So what does the inspiration tell you? Well, this is the model. It's the Nomoto model number 1. And you want for the true output to follow a certain reference command, RC. So you are obviously interested in making the error between that guy and R, which I call E, go to 0. The simplest strategy that you can think of, it's the most stupid and naive controller that you can think of, is, well, when the error is large, here, then I multiply by a certain gain and I feed the rudder, and so on and so forth. So this is a very simple control law, naive, that you simply put the gain here and see if this works, right? Okay. The first interesting thing is the following. So in fact, we are doing U equal to K RC minus R. That's what we are doing here, right? So when you put this together with R dot equal to minus AR plus BU, something interesting happens. You get minus AR plus BKRC minus BKR, right? So you get R dot is equal to minus A plus BKR plus BKRC. So whereas before you had R dot equal to minus AR, and that was associated with the intrinsic damping of the system, now you have R dot equal to minus A plus BKR. So you have added damping, which makes sense because see where the natural damping comes from. You have R multiplied by a number and you feed negative. And you are doing exactly the same here. You have R multiplied by a number negative and you feed it. So this is like a virtual extra damping factor. So what you have accomplished here is, if you were not too happy with the natural damping of the system, because I told you that if you don't excite it, then you get e to the minus AT. And you know that if this number is small, it takes a long time to decay to 0. If it is big, how do you make it big with this control system that you have here? So there's a way of controlling the damping. I mean, it's not earth-shaking, but it's interesting. So now in fact, you have R of t equal to R of 0 e to the minus A plus B K T. Okay? So you increased through that action. So what happens here? If this number K increases, if it goes up, right? Then, oops, I'm still learning how to operate with this. Then the damping goes up and R gets down to 0 faster. You know, you slow down the rotation very quickly, more quickly. Now you could say the practical aspect, this is not, I don't see a practical application, because if you have a bolt out there and you have it rotating, I mean, and having it stop, it's not an extremely good thing to hope for. I mean, but it's just an example. So what I'm saying is that if it is rotating for some reason, going at the forward speed, and if you want to stop the rotation, then you do this feedback and you increase the damping, it will go faster to the origin. But there's a price you are going to pay, because at the input to the plant here, okay, you'll have the error multiplied by K. And if in your attempt to make this very fast, you increase the K, then the input to the plant is going to have very large numbers, and the rudder may have deflections of 100 degrees, or which we cannot achieve. So there's a price that you have to pay, because as K goes up, then you may become quite large. Quite large. So here you already see something interesting, because from a theoretical standpoint, there was a breakthrough in the design of control systems when people understood that the framework could be that of game theory. And in game theory, as you know, there are in one of the simplest form two players, and they are playing against each other, so things like that. And that's what we are having here, because on one hand, it's not exactly the case, but on one hand, you want to make the system faster and faster, but there's someone else that tells you cannot go that way because you end up deflecting the rudder so much that this is not possible. You have to be careful. But other than that, things look okay. All right, so you go there, implement this system, and it should be fine. So what's wrong with this? Let's ask a very simple question. With this control scheme, what happens when you tell the rate of rotation to go to a desired value that is constant? I want this guy to rotate at a certain rotational speed that is RC star. What do we know? You see, you have these things exponentially decaying, so the system is stable. So it can be shown, I'm not going to get into that, it's not terribly important, that when you excite this system with a reference, things may wiggle a little bit, but the output is going to go to some point because the system is stable. So believe me, okay? So the system is stable. This implies that R of t, as t tends to infinity, is going to tend to some steady state value RSS. Okay, now, and what is this value that I get at steady state? Now, again, remember that I have R dot equal to minus AR plus BU, and U is equal to minus KE, right? So you have R dot equal to minus AR. Did I do something else here? Yeah, minus R minus BK R plus BK RC star. Should be something like that. So now, suppose that you have reached the steady state. So when you reach the steady state, the derivative of this is 0. So you get minus AR steady state minus BK steady state, and that one is fixed, of course. So you have BK RC star. So reach the conclusion that R of SS, if you solve this equation, it will give you BK. Oh, Coena is here. Interesting. Okay, BK over A plus BK RC star. Now, this is very disturbing. Why? Because you would like for this number to be 1. In other words, when you have RC, you would like for, whoops, at steady state to have RC. So this should be the number 1, and it is not. So you have BK over BK, A is greater than 0. This is always less than 1, okay? So unfortunately, this system does not work very well because when you excite with RC star, R is actually going to settle at the value that is below, right? When is it that RSS approaches RC star? That's when K blows up to infinity. But you don't want this. Then RSS goes to RC star. This will not work. Okay. And you need this. There are people that reason in the following way. Well, I mean, if I want to reach RC star, and I know that RSS will go to RC star multiplied by this value, then when I give the command, I compensate, and instead of having RC star, you give RC star divided by this one, and then you get RC star. But that's cheating, because it means that you have to know exactly the A and the B. And in many cases, so you don't want this. You actually want very high accuracy on this thing. You want the guy to be dead on RC star. Now, you may ask the question, why is that so? Why is it that I'm not able to have the output go exactly to RC star? And the truth of the matter is you can't. And this is one of the interesting things that you have to understand. And sometimes people avoid this subject because, I mean, it's obvious they don't mention it. But you should ask the question, why is it that the output cannot go asymptotically to the value that I wish? And the answer is very simple. So I'm going to call the system that you wish to control G, so that I don't have to keep writing it, right? So you have the U here, and you have the R, and then, oops, and then you close the loop, and then you have the K, and you feed. So here you have this thing over there, and you feed in RC star. So why is it that we cannot make this guy go to RC star? And I'm going to reason by contradiction. I think in some people use the Latin word ab absurdum. Okay, let's not get into that. Yeah, it's a very nice word, ab absurdum. So suppose you can actually, for some reason, have RSS equal to RC star. Suppose you can achieve that. Okay, but if this guy is exactly equal to that guy, then E is equal to 0. And when you have 0 multiplied by K, you have 0. So this system is dead. It's a stable system that is driven by 0. You get 0 at the output, which certainly is not RC star. So it's a major limitation of the system. There's no way there's no way you can do that. So it's like the snake biting its tail. In order to have something at the output, you need something at the input, so you need a certain error. You are doomed. That's what this means, right? Okay. So how do we get around? Yeah. No. I'm saying, let's assume by contradiction that with the control system that you have, that is very simple, it's just a gain, that is shakes up a little bit, reaches steady state, and the output is exactly equal to RC star. You are dead on. In that case, the error is 0. And 0 times K is 0. Now you attack this system by 0, you get 0 at the output. So you cannot possibly have RC star. Is that okay? This is very simple, but it's very, very important. Okay. All right, so it's very intriguing. So then you ask the question. So I have 0 at the input. I cannot do this. What value would you require at the input at steady state? I'm looking at the notes. I'm still not familiar with this process of going from one to the other. What value should you have at the input here, such that at the output I get exactly RSS equal to RC star? That's the question. Okay, so remember that I have R dot equal to minus AR plus BU. And I'm asking, what should this value at steady state be, such that RSS is equal to RC star? Okay. So what you do is you put RC star here, RC star dot equal to minus ARC star. No. Yeah, this is okay. This is okay. RC star plus B U steady state, right? And from here, you reach the conclusion that if you put at U A over B RC star, then the output tends to RC star. Which tells you the obvious. In order to have RC star here, I need some action there at the beginning, at the input. I cannot have 0. And this is exactly the value that you have to have. Okay? So this doesn't work because you have 0, and then you would hope for other. How do you have the sign? What is the sign for hope for? I don't know. Something up in the clouds. I don't know. You would hope for this value, USS, to be A over B RC star, and it is not. How can you make, given that the error is 0, how can you make USS equal to something different from 0? This is freaking weird because K is a finite number. So when you multiply by 0, you get 0. You don't get that. This is at steady state. Okay. What is the dynamical element that at steady state gives me infinite gain? You need an infinite gain to have some form of raising the indeterminacy. Okay, so the question is, what's the dynamic system or element that gives you infinite gain at steady state? Sometimes people say at frequency 0. Okay, let's look at the integrator. So if I have X, you have Y, right? And suppose you start this with some charge. So even if this is 0, the integrator will keep, it has memory, and it will keep the value Y0. But seen from a gain point of view, you have Y0 divided by 0 gives you infinite gain. It's a remarkable element that has memory of the past and gives you infinite gain at frequency 0. If you wish, you could also think differently. You could say, for example, okay, this is too confusing for me. Let me excite with a step. And then you know that this will give you a ramp. And steady state is there. Infinity divided by that guy gives you infinite gain, right? It's the same way of doing this. So it seems that the only pass of magic that you can do in order to have 0 and something finite at the output, you have to have an integrator there. And the integrator has to charge up to a certain level, and we'll see how that is done, so that when the error is 0, the integrator holds on that state and keeps it there and feeds the value that is required to drive the output to the desired value. This is what people call integral gain. That's what it is doing. The integral gain is simply this. It's a memory of the past. It holds the memory of the past. So even when the error is 0, the integral has learned a certain value that keeps there, drives the plant, and drives the output to RC star. Exactly. Yeah.
So why can't we code it in such a way that when the error becomes 0, so don't push the decision loop and then keep maintaining the same state?
You know, in control, it's not good to have ad hoc strategy. No, not necessarily so. I mean, even when, okay, so suppose it goes through 0. So when you are at 0, oops. So see, so suppose this is 0. I don't follow you, because if he's 0, this is 0, and then the output is 0. Maybe I'm not following your reasoning.
infinity, like where they gone to the destination. So then after that, like if we can maybe modify the code such that.
But that's what the integrator does for you. Things wiggle a bit. The output goes to RC star. In the meantime, in the process, the integrator has learned the value that is required to drive to RC star, and then it doesn't care if the error is 0. That's exactly what the integrator does without any logic embedded in the process. That's the beauty of the integrator. Okay.
Why not add the bias like A by B RC star, since RC star?
No, because it's a brute force method. What if A, B are not exactly what you think they are? That's always the problem. Okay, so remember that there are two things. There are open loop control strategy, which is what you are talking about, and closed loop. Open loop strategies are not robust with respect to parameter variation, so you cannot use those tricks. Okay. If you know the plant very well, then it should be fine. Okay, we were here at the integrator. So the integrator, bear this in mind. The integrator is a okay. I told you about my advisor, Professor Pramod Khargonekar, and I mean, it's very well known. He has an outstanding work in the most contrived things. Yeah? And one day, a couple of years after I graduated, we met, and we were having some tea, I believe, or coffee. I don't know. He said, António, after all these years, I reached the conclusion that one of the most important contributions of control theory is the integral block. He said, what are you talking about? You know, he is right. I mean, it's such an interesting thing, so simple. And as you'll see, it solves a lot of problems. Okay. So how do you do this? Well, if the integrator is not there, let's put it there. So again, now you have this block, which is the system that you wish to control. I'm going to call it G, and then you have R, this is U, and I'll put an integrator there. And then you have K, right? And this is the error. And now what? And now you do this, and you have RC. And you have what we call integral action. Now, is this going to work? The first thing that you have to analyze is if the system is stable. That's the first thing. Okay, so you start with this dynamic, sorry for repeating again, minus AR plus PU, right? Okay, so if you differentiate, you get double dot minus AR plus B U dot. But this U dot is this guy over here, because this is the derivative of the other one. So of course, U dot is equal to K RC minus R. Okay, right, so if you put it there, you get R2 dot equal to minus AR dot plus B K RC minus B K R. So you get plus AR dot plus, oh, sorry, this is not RC. Oh, yeah, it's okay. Plus BKR is equal to BKRC. This is a second order system. Stability does not depend on the right-hand side. That is the excitation. It only depends on this. I don't know if you know, but if you have a second order system and the coefficients always all have the same sign, so this one is 1, it's positive. A is positive, B and K is positive. If everything has the same sign, the system is stable. So if you start with R and R dot, will go to 0. So the system is stable. So that's fine. So if RC goes to RC star, so that's one good thing. By putting the integrator there, we are not destroying the stability of the system. Now I have a set of computations here. Let's see if I don't get lost in the process. But it's important to show you. Okay. So let's look at steady state, because we know the system is stable. So when you excite with RC equal to RC star, the R is actually going to something that we call the steady state. So you have steady state, second derivative, plus steady state, plus BK R steady state equal to BK RC. So if you are at steady state, this is 0. And now see that RSS equal to RC star. Beautiful. So that's what you get. Now you could ask the question, and what is happening to U? I mean, it can be shown through computation, it's there, and then I will leave the notes with U. You can actually show that this U is going to charge up to the value that is required to drive the output to RC star. So somehow, when you switch this system, it starts jiggling, the integrator does something, charging, and then suddenly this guy starts going to RC star, the error starts going to 0, but the integrator will hold the value that is required to have the output go to the input. That's the magic. So you see how this is operating. Now, it's very important to understand this because it's one of the magic blocks. So how does this work? So again, I think I made a mistake here, but no, R dot plus RR. No, this cannot possibly, just a sec. No, better not do it that way. So what's going to happen intuitively is the following. This is time, okay? And you excite with RC star, RC star. And we have shown that no matter where you start, because the system is stable, this guy may wiggle a little bit. This is RS that R that I'm plotting, is actually going to converge to RC star. All right. Now this is very interesting because the error, which is quite big at the beginning because R is equal to 0, so you're excited, the error is large. Now, the moment the error is large, you multiply by K and you start pumping up the charge on the integrator. That's the important thing. So the error is large, so the integrator will start charging. All right. And because the integrator is connected with the input, this guy starts going in that direction. All right. Then the error will start decreasing. We do something like this, but the integrator may do some fluctuations. Now, when this guy gets small, it is not as steep. And the integrator is going to charge up to the correct value required to drive the output to the desired system. That's how it works, okay? So it's very important to understand this. Integral action. It's a magic block that it has the effect of, you hear this expression, it drives the steady state error in the response to a constant to 0. Okay. And let me tell you something that is a general lesson. And yes. No, not the input. It's acting on the error multiplied by sending and then goes through the rudder. Am I missing? No, maybe I'm not seeing it correct. So this is the Nomoto model. The output is R, the input is the rudder deflection. So I do feedback, compute the error K, and send this through an integrator. Huh? Yes. Yeah, the input to the integrator is K times E, correct? Is it okay? Okay. Let me state a very general result. When someone gives you a control system, and this one is simple, it could be more complex, it could be a lot of paraphernalia here and stuff. Suppose it is stable and you input a constant. Question, is the output going to go exactly to what you desire? And the question is very easy. When you analyze the top stuff that is called the open loop, and you see at least one integrator, that result applies. Because the integrator, an isolated integrator, in other words, doesn't have a local feedback. So when you have a control system and you look at the upper chain or link and you see one integrator isolated, if the system is stable, the steady state error is 0 exactly, which is quite nice. Okay. Then I'll mention this again. Yeah.
What do you mean charge on the integrator?
What I said was the following. The integrator is the intelligent block. It's not very intelligent. Let me go back to the diagram. What the integrator is doing is the following. Well, I guess this, I'm still not used to this. So you input this, and this starts wobbling. So when the error is large, the integrator starts increasing. That's what I mean by charging up. Okay. And it feeds you to R. R will increase. But as R increases, the error decreases. And the integrator starts coming down. And then again, it goes up until everything settles. And somehow the integrator in this process, after fluctuating a bit, learns the value that is required, even with 0 here, to have the output exactly equal to the input. Is that okay? No. Is it? I think that there's at least one question here. So in that case, the actuator delta will always be at some value that is not. What is delta, Avanish? Huh? Yeah, of course. Otherwise, you don't rotate, right? Yes. Yeah, I have an issue. The rudder has to go to the angle required so that at steady state, you turn with a certain rate, correct? Yeah. I'm going very slowly. I have to speed up. Okay, and now I should kill this thing. And any other questions at this point? Okay. So now if we have this beautiful system here that is stable and ensures that when you command the rate of rotation to go to a value, to actually go to that value, how do you choose the K? How do you choose the K? All right, you have to have a way of choosing the K. Okay, so think of the mass spring dash pot. So the original system is R double plus AR plus BKR equal to BKRC. That's your system. Second order system. How do I choose the K? Now, notice the analogy with the spring, with the constant Ks, the dash pot with damping beta D, and then you have the mass, and this is excited with the force. So I'm not going to waste time deriving the equations again. I mean, we saw that before. So the equations are x2 dot, where x is the displacement, x2 dot plus beta d over m x dot plus ks over mx equal to f over m. So what we know here, this term here is due to the spring. So the term in X captures the spring effect. The other one is due to the damper because it multiplies the speed. So this is a damper effect. And so you know, so you know so much about this stuff, right? So I don't know if you know the so-called canonical form of second order systems, maybe not. There are ways of writing this so that you get a nice physical interpretation, which is x2 dot plus 2 psi omega n x2 dot plus omega n square equal to something on the right side. Okay, let's not get into this. What I know is that when the spring is very tough, then the system is going to do a lot of and the natural frequency of oscillation gets higher and higher. That's what it's called, the natural frequency of oscillation. And I also know that when the damping factor is large, then you get more damping. So instead of having something that takes a long time to get down to the final value, it's relatively smooth. So you know more or less, I mean, because now look at the beauty of this. What do you know? This guy here is going to act as a virtual spring. And that guy is going to act as a virtual damper. And that's, you should get used to looking at things this way. So what do we know? I don't know if you have learned yet what we in electrical engineering call the body diagrams. You call it something else. Well, huh? The body plots, exactly. Okay, so for this second order system, this is great. So you know very well that omega n, the asymptotes cross, and that at low. And then you may have something like this, starts going up, it starts shooting. And this is as psi goes down, as the damping coefficient goes down, or as the damper coefficient goes down, then you get these peaks and stuff like that. But the important thing, for example, is that as you increase this Ks, or as you increase your gain K, this region of frequencies over which your system is going to react gets larger and larger. This is very important. And that's how you choose the K. Because when you have a ship doing maneuvers, like so, when you design the control system, I mean, this RC is not going to be fixed. It's not going to be constant. And you ask yourself the question, what is the richness of the input signal? Is it going to be very jerky or not? And ultimately, you have to say something like, the maximum frequency at which I'm going to excite is something. So I don't know if you have this intuition, you should have it on your mind. Why do we talk about frequencies? Imagine that RC is a periodic signal. Then you do this Fourier series. So what you are saying is that if you have components up to, I don't know, 1 radian per second, you would like for the output to react and follow very accurately. So in this case, when you plot this diagram, oops, this guy here should have at least 1 radian per second. And that's how you choose the K. So the person that orders the controller said, design me a controller to stabilize steady state error equal to 0. And look, the signals at the input are going to, people call in terms of spectrum, are going to have a spectrum contained between 0 and 1 radians. So don't expect anything terribly nervous, but between 0 and 1, for example, the output should be able to follow with good precision. Then you have to design this K such that this region here over which you may get something flat, if the damping factor is not too small, should be at least 1 radian per second. You know, when you do something here, then the other guy follows with good precision. So that's how you design the K. Okay, now we have a serious problem here because, whoops. All right, so I'm going to repeat this, R plus AR dot plus BKR equal BKRC. And from this analogy that we have here, we know that this is 2 psi of omega n, in which omega n is this frequency at which you cut. And psi is the damping factor that tells you if you have overshoot or you don't have overshoot. What are the rules of thumb? You should have psi, I like psi around 0.7. So it's not extremely sluggish. So it has some small overshoot, but it does not pick up. So psi equal to 0.7 is a good thing. What about omega n? It depends on your application. If the person that ordered the system wants the system to follow signals up to 1 radian per second, which is huge for an electromechanical system, then omega n should be that fast. So we know psi around 0.7, omega n, whatever you want. So this is 2 psi omega n, and this is omega n squared. So if someone tells you, look, I want my omega n, this sometimes is called the control bandwidth. Control bandwidth, that's the name that people say. So here is omega n, 0.1 radians per second. Okay, you do the count, all right. So you want BK to be equal to omega n squared. B is given, so K is equal to omega n squared over B, and you are done. You'll be able to get this bandwidth, right? Aha, but now you have a problem because 2 psi omega n A is equal to, no, 2 psi, this is wrong. 2 psi omega n is equal to A, right? And A comes with the system. It's not something you can change. So this means that when you choose K to meet a certain bandwidth, you are doomed because psi is going to be A over 2 omega n, which is A over 2 square root of KB. So, very important. If someone asks you for a large bandwidth, you pump up the gain. As you pump up the gain, you are doomed. Psi gets very small and boom, it's all oscillatory. And there's no way you can control this. So it's not a good design. So this is very interesting because it shows you, and you know why is it intuitively expected? Because when you have a second order system, you have to control omega n and psi. And you only have one design parameter, which is that gain. I always have time. You only have one degree of freedom. You have to have another degree of freedom to be able to control this thing exactly. So this is not a good design yet. All right. So so where's the other degree of freedom? So I'll let you guys suggest what should I do. So the problem is I may not have enough damping because the psi is very small. I have to increase the damping. How can I increase the damping on this system? That's the question. So I don't know if any of the guys out there wants to, oh, there are questions. For some reason, I cannot see this. No. No, I don't see any questions. But here I see two. I don't know. Okay, are there any questions from people online? So this is a challenge. What should I do? I have to do something about this. How do I make the damping higher? Okay, so the secret is very simple. Remember that the damping effect is something proportional to the derivative of a signal with a negative sign. All right, so again, if you want something and it is not there, you have to put it there. So this is the system, this is R, this is U, this is the integrator, this is K, this is RC, R. Not enough. So how we do introduce another damping? I'm going to change the notation because here I only had one element. I called it K. Now I'm going to call this one K2 because I want to introduce another K. All right. You have to introduce in the action that goes to the rudder something that is proportional to R with a negative sign. That's how we introduce a virtual damping. So the only thing that you have to do is the following. Okay, I go here and I add K1. That's it. It's very important to understand this, all right? So this is extra artificial damping. Beautiful. Okay, will this work? I don't know if I have the courage to make you go through the expressions, but I'll do this very quickly. So now you have R dot equal to minus AR. If you understand these cases, this will help you a lot in the future. And U is equal to minus K1 times R, minus K1 times R, and plus something I'm going to call psi, which is the output of the integrator, plus psi. So what is psi dot? Psi dot is equal to K2 RC minus R, right? So you're okay. You have one integrator inside, R dot equal to minus AR, that's that sets, so, you know, and you have another integrator there. So it's a second order system. So you should be able to write the whole thing as a second order system. So this I do by computing the second derivative of R, which is minus A R dot plus B U dot. So this is minus A R dot, sorry for going fast, and U dot is minus K1 R. So you get minus B K1 R dot plus B psi dot. Okay, so this is, so you get minus A R dot minus B K1 R dot plus B, and now you go for psi dot. This is becoming complicated. K2 RC minus bk2r. And finally, you get double. And now you collect the derivative bk1r dot plus bk2r is equal to bk2rc. Notice now. Before, we didn't have this term. We only have this term that we called K. So we could control the omega n. Now you have an extra term. And you can control with it the damping. So now you can control the psi and omega n. So no matter what diagram you give me, I'll be able to make the system do that. So you can have a large bandwidth with sufficient damping. Of course, okay, so of course you shouldn't be too happy because, and this is always very important, when you design a control, someone comes to you and says, I want you to design a control system such that the bandwidth, we already know what that means, that's this gap here, is, for example, omega n equal to 0.1 radians per second, and I want the psi equal to 0.7. Okay, so you say this is omega n square. You design the K2. And now this is 2 psi omega n. You already have the omega n. You want psi 0.2, so you choose the K1, and you are done. It may very well be that if you choose an omega n that is very large, so you have a K2, K2 will be extremely large. And when you give a reference that is away from the initial situation here, this thing gets very big and suddenly the rudder will saturate one side or the other. So you have to be careful about that. So, and this is something you have to study. Okay, it's important. So always bear in mind that hidden in here, it's something that I did not write explicitly, but it's very important. When you tell the rudder to go to 5 million radian, it will not go there. The rudder is limited, let's say, I don't know, 20 degrees minus whatever. So remember, you have this block here. It's a saturation. So above a certain level, it saturates, let's say, to 15 degrees or minus 15 degrees. So if you excite this system and in the process, it hits the rudder and the rudder, toing, 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 this will not work well. So the question is, what do you do in order to avoid touching this stuff, right? So that there's a couple of ways of doing this. I'm going to show you a way that people use all the time. So I don't know if you use that in your PID controller, something called anti-windup. Did you use that? Yeah, no, but the anti-windup scheme did, huh? It's very important. Okay, anti-windup. That's a strange name. But it's a brute force method. I mean, people don't know exactly how to design this. There are other ways of designing this, which is using more modern tools. There's a buzzword called model predictive control, where you design the control law, and then at the same time, I say, yeah, but the input should not exceed something up or something below, and it generates the control law, but it's more complex in terms of implementation because you need to solve an optimal problem online. So I'm going to teach you how you deal with the anti-windup. So, all right, let's go through the anti-windup and then we'll wrap up, okay? Because otherwise there will be too much for tomorrow. I'm curious, is there a way? Is there a way we can have a copy of this stuff? No, I don't think so. Is this recorded in the memory? Oh, this is wonderful. I'm so primitive. Okay. Now, sometimes it's a bit, it's not a complicated thing, but it's not very intuitive how one does that. Okay, so how do you implement the controller? You have this, R, you have you, and sometimes you implement it in this manner. Okay, so you have RC, and then you have R, and remember that you have an integrator here, K2, and then the integrator. And you have another block here, K1 times R, that goes in there. So sometimes people put it up there. It's not the best way of doing it, by the way. But you see this implementation a lot. It's called P. So this is error. It's something proportional to the error. So it's proportional control. And this one is the integral control. It's PI control. So now you have a problem, because if this guy here has a saturation, if you give a command that is very large, the error is going to be very large. This thing pumps up, saturates immediately. And now something very dangerous happens, because when you saturate the rudder, you essentially are in open loop. I mean, you are not doing anything wise. You're like, boom, to the side. You lost all the control authority over your ship, okay? And you lost all the control authority, and the guy keeps saturated. And the error keeps being large. And the integrator keeps charging. It's so much ado about nothing. It's doing all this work and it's useless. Finally, when this guy crosses RC, then the error gets, in the region of 0, and the integrator then starts coming down, and this gets in the linear region, and it may go the other way. So what you do, what you end up obtaining, even though you designed a control system for which psi is good, you'll end up doing large excursions that are caused by the fact that the integrator is doing work for nothing. Because again, I repeat, when this thing saturates, you are open loop. I mean, this guy is disconnected from that thing. But you still have an error, and these guys keep charging and pumping up. So the integrator is now doing the job of charging and discharging, but not for the noble reason of driving the steady state error to 0. It's charging. So you've got all these fluctuations. So what is the solution? Please stop that guy when I hit saturation. Don't let the integrator go wild and charge up or discharge. So this process of charging and discharging is called the windup. I don't know the origin of this word. I know that when you have a kid and you say, oh, the kid is completely wound up. Say the kid is on his own, complaining about. So I don't know if the name comes from there or not. I have no idea. Or maybe it's from winding up something. I have no idea. So the question is, how do you kill this? Now, this is very interesting, and I'll stop here. So this is the integrator. No. Why do I want to erase with my finger? This is the system that you wish to control. And you have R over here, right? So. And you know that here, somewhere hidden at the input, you have this saturation, right? So please don't let this signal go much above or below that saturation. So the way people to do this is the following. So you implement this, you have RC, you have E negative. So now you put this stuff, K2, integrator, and it goes here, and then it goes there, K1. By the way, this is not the way we should implement it. There's a more nicer manner of doing this, and now it becomes the important part. If you were to connect this directly to that guy, the input here could go above or below. So don't do that. So essentially, and this is the trick, whenever you detect that this signal goes above or below, try to bring the charge of the integrator down or up, as it may be the case, so that it does not keep pumping up or pumping down. So you do a replica of your saturation, because after all, you have a tunnel here in which the system should work. And when you go above a certain level, it's not worth doing anything, because this can only take this, whatever goes through the tunnel. So better shape things at the input so that you don't cross the boundaries. And now you do the following. You compare whatever signal you are generating with the saturated version. Okay? And now, if you are in the linear region, there is no difference, and you do nothing. But for example, if this system is starting to get larger than the maximum, then you get the positive sign, and you should tell the integrator, please calm down, be a good boy, okay? So now you have here this, you send through a gain that you have to decide what that gain is, and then you insert it in there. That's the famous anti-windup scheme. So please hold the horses when something starts going waywire. That's the famous anti-windup scheme. Question, how do you design A1? I don't know how to design it. I mean, it's mostly by trial and error. Yeah, but this may save your life, because it prevents these weird oscillations up and down. Okay. So then I'll continue now with the Nomoto model number 2, which will be slightly more complicated. And when you get to the Nomoto model number 2 and you want to do other things, then you get into a system of order 3. And then we don't know how to design the controller, because it's an equation of order 3. There is not much intuition. And that's where I tell you, okay, don't panic, because there is a fantastic tool out there that will allow you to tackle more complex systems without much hassle. Beautiful, you just solve an optimal control problem and the gains will come out very easily. Okay, so any questions, please? So first from people back home, are there any questions? Yusen, is this alien to you? I hope not. No, nobody's alive out there. Okay, any questions from the audience here, please? Too confused? I hope not. No. Okay, so if there are no questions, a very important announcement. So tomorrow we'll have to start at 2, right? So for everybody out there, so tomorrow we'll start at 2 in India, of course. Okay. I don't know if there is a way of sending an announcement to everyone or something. Okay. Okay. So thank you for being persistently exciting and coming here. It's good. So tomorrow, I think you'll be delighted with the tool that I will be presenting. Okay. Okay. Have a good evening. Bye-bye. Yeah. Okay. Bye, everyone. Oh. Ah, it is very different from what I learned. Okay, okay. Well, we'll talk about that.